Right, let's start the next lesson now. Induction. Got that? Matt, yeah? And okay. Let's see how we get on. So we've seen that a moving charge in a magnetic field will experience a force. What happens if we move the magnetic field? So here's a again, a simple experiment. What you do, you have a voltmeter, you wrap the voltmeter around this copper pipe, and then you move a magnet in and out. And what you notice is that you actually get a voltage. So if you apparently move a magnetic field around some conductor, like a copper wire, you'll actually make a current, a voltage in the copper wire. This is called electromagnetic induction. Now this is actually very, very important because this is the physics idea that lets us make electricity. Okay? So if you're wondering how do we make electricity for our homes, it's using this idea in physics called electromagnetic induction. So what happens is in the power plants, they move giant magnetic fields around conductors, and they cause a current to move in the conductor. Now you might say, how do they move it? Well, if it's a wind turbine, then the wind can spin a magnet. If it's coal, they can use the heat to make steam that can turn it. So this is really, really important for what would you call engineering of, energy engineering, like green energy or energy and all this. Is any of you doing that? What are you still wanting? Say again? Biomedical? Which one? Oh, okay, and applied physics. Yeah, I think this would be probably most relevant for applied physics. So if you can draw this and write its name underneath it, electromagnetic induction. In your picture, can you just add maybe a little arrow that says move this and this moves? Just something like that. Did you draw this? You draw it. Okay. Continue? Yeah? Andek?
Yeah.
Yep. How many of you have seen this before, electromagnetic induction? You've seen it before? Okay. Who cycles? Who has a bike? Do you two? Yeah. Do you have a little light on it? No, you don't. Oh, that's very naughty. Some of the bicycle lights, you can connect them to your wheel, and as you cycle it, the light shines. Because you are actually spinning a magnet inside the lamp, so it makes the electricity for it. Okay. So here we move the magnetic field, we'll get a voltage. That's electromagnetic induction. So just the formal definition, electromagnetic induction is the production of a voltage across a conductor when you expose it to a change in magnetic field. So if there's any word here you don't know, just tell me, but I think these are all words you know. Is this okay? The English is okay here? Continue? Got that? Great. Basically, induction means, my typing is so bad, producing a current by changing a magnetic field. Now, so we have two laws regarding it. Okay, so the first one is called Lenz's law. And Lenz said that if an induced current flows, the direction is always so that it opposes the change which produced it. So I can explain that better with a picture. So this is what Lenz noticed. Here, we move the magnet into the conductor, so the north enters in here. And what will happen is you'll get a current, but the current moves out, back. If the magnet enters here, then can you see the current tries to come out here at the back end. So if we enter at the back end, the current comes out at the back end. And here, so here I'm pulling the magnet out. So the magnet is coming out of this end, it's coming out, which means the current is going in at this end. Okay, so here, if the magnet goes in, then the current comes out. If the magnet comes out, then the current goes in. This is called Lenz's law. The pictures, I don't know. I don't know which is better for you, if you write the definition or if you draw the picture. I'll let you choose. Okay, so you need either the definition or the picture, one or the other. So what did you opt for? Siba, definition in words or in picture? What did you pick? Words. Matt? Both? Good for you. And Andek?
I want to do both.
You want to do both, okay. Now Siba, do you feel peer pressure to do both, or you don't have to, seriously? One, okay. Got that? Yep. Andek? Yeah, no problem. No problem. Matt, you have this? Yeah. Have you seen this law before, Matt? Lenz's law? No? Huh? Oh, okay. You've seen the picture before, yeah. Have you seen this before? Now, this actually, Lenz's law is important for some safety at home. Do you all know those extension cords, you know, the ones that are wrapped up in the wheel? Do you know these ones, Matt? The extension cord is wrapped in a wheel. Yeah. It's very, very dangerous to connect this to something that's very powerful, like some powerful garden equipment, and not to unwrap it. Okay? Because the reason is, if you have it wrapped up and you have it connected to something powerful, then you'll have a very strong current here. Okay? Lenz's law says that you will make a magnetic. Okay, so there's a few things that are happening. When the current moves in the wheel, it makes a magnetic field. Okay? This magnetic field and the current are in opposite directions. So you might say, well, so what? Well, what will happen is the wire that's on top, it produces a current, a magnetic field. This magnetic field will try to move the current underneath it, but because it's in opposite directions, it basically tries to prevent the current from moving. So if you have all your wires stacked up, the magnetic field that's made on the top wire, it tries to push the charge in the opposite direction on the wire underneath. So in effect, you'll have more resistance than you need in the wire, and the wire starts to heat up. So actually, if you're ever using one of these wheels and you have it connected to something, it's really a good idea to fully unwrap the wheel for safety. Otherwise it'll overheat. Okay, so Lenz's law is actually the reason for this. Okay. Next now. So next one is Faraday's law. So far we know that a moving magnetic field will cause a current to flow in a conductor. And we know the direction is the current is to oppose the field. But we don't know how to calculate the voltage. So Lenz's law just tells us the direction of the voltage, but it doesn't tell us how big it is. So that's actually Faraday's law. So Faraday says if you want to calculate the voltage, then you just need to calculate this. If you want to calculate your voltage, it's equal to this. Now, just before you write that down, just to explain some things here. The reason for the minus sign is actually Lenz's law. So that minus is just because of Lenz's law, and the voltage will be in the opposite direction. This here is the change in the magnetic field. This is how quickly it changes. and the n here, the n is the number of loops. So I think the minus is in fact Lenz's law. Now this will only make sense when we do an example. So if you want to write Faraday's law down, we'll do an example later. Got that? Continue? Continue? Yeah. Okay. So, continuing. And that, yeah? So, if we move a magnetic field around a conductor, or a conductor around a field, then can we use this to generate power? Yes, we can. This is how we do it in a power plant. So this is called the AC generator. It's the most common generator in the world. I don't know if you can really see the picture. So I'll just explain the parts. So here you have a north magnet, and here you have the south end. And here you turn this wheel. So this guy turns around. Now, this side is connected to a ring, and this side is connected to a ring. Now, they're connected loosely. What I mean is, you have your ring, and they're connected, and they touch like this. So when it turns, it just brushes against the ring. Now you might say, well, why don't you just connect it directly? Well, you can't, because if it turns, then the wire will twist up. And that's the end of it. So there's usually a little brush, and it's brushing the ring here. So you can picture, as this is turning around, you see this little guy here? That's running inside the ring. Okay? And the same for the other one. What you'll actually make is you'll make a current. So this is exactly how they make power in a power plant. They have a big magnet, north and a south, and they have this square rectangle with the current, with the conductor at either ends, and they just turn the wheel. And as this turns around, it's the same effect as turning the magnet. You know, like if I said, here's the copper wire, here's the magnet. If I move the magnet, I make a current. But which is easier, moving the big magnet or moving this? Well, moving this is easier. So you can either do this, or you can keep this stationary and then move this. It's the same effect. So that's what they do in the power plant. They move the copper wire around inside the magnet and they generate power. So these guys are brushes. These are called slip rings. And this is the resistor here. So in your bicycle, the resistor would be the lamp. Okay. Again, they could ask me to draw this, so please do your very best to draw this with the names, okay? drawing beautiful AC generators? Yeah. Let's see how well you're drawing these. That's all right. Don't do fine. Carbon brushes, we need to label those. Not too bad. Not too bad. Where's yours? Not too bad. Yeah, good enough. Slip rings and brushes. It's okay. Good. Right, can I continue? Yeah? So, remember we said Faraday gave us this formula, voltage equals minus N delta flux over delta time. Now, remember we have the formula B equals flux over area. So that means flux equals BA. Okay? So flux you can replace with BA. Now let's not worry about the minus N for a moment. We don't care about the minus N just for a moment. Because the minus is for direction and the N is how many looped wires there are. So I won't worry about that just for a moment. So how does the BA change? Well, the normal to the plane, which is rotating, makes an angle theta with the field. So, okay. We need to add a cos theta to the BA. I don't know if you... did we talk about cos theta in the last lesson? Maybe I skipped that slide. Maybe I skipped over that slide. I'll just write it down here for you. So, remember we said, slide must have been skipped. So, here we have B equals flux over area. Yeah. However, we want this to be 90 degrees. Okay, so you could probably guess what happens if it's not 90. So let's say it's like this. It's at an angle, like that. What do you think you do if you want to calculate the B now? Well, no surprise, we still have to look at the component which is perpendicular. Okay, we usually measure the angle this way. So if it was at an angle, the formula simply becomes B equals flux over area. Sorry, let me just write here. Flux equals BA, and so flux would equal BA cos theta. So if the theta was 90, it goes back to being just BA. Okay. So I think this is clear enough. Just before I continue, it wouldn't be a bad idea if you add this to your notes. So this is if not 90 degrees, e.g. theta degrees. So we use this formula. This is the normal. Okay, can I go back to my slide? Yeah, I think we'll just finish on this slide and we can continue it next time. Is it okay, Andek, or do you need a minute?
Yeah.
I can go back?
Yeah.
Okay, so we need to add cos theta to the BA if it's at an angle. So we have BA cos theta. So this is BA cos theta, because what's happening is, because the machine is turning, it means the angle is changing. So we have this, BA cos theta. But the BA is constant. the magnet doesn't change and the area doesn't change. So the only thing that's changing here is the cos, because the theta is changing. Yes? This should remind you of something you did in maths class. I have the change in cos. What does that kind of remind you of? It's a bit like derivative in calculus. You know, this is a bit like derivative of cos. How does cos change? What's the derivative of cos? It's sine. So in other words, this is what the graph of the voltage looks like. As you turn the wheel, the voltage increases and then decreases. But the shape it makes is exactly a sine graph. Have you seen your sine graph? Okay. And here I have the positions. So if you start off like this, you get no voltage. And then as you start to rotate it, you get most voltage at 90 degrees, then back to no voltage at 180, and then negative voltage at 270, and back to 0 at 360. Okay? I have seen in the exam, they sometimes ask the students to draw the voltage with the positions of the generator, which is what I have down below here. So as soon as you draw that, we'll finish for this morning. So, imagine I could connect a voltmeter to this in here, a voltmeter, and I connected the voltmeter to the computer so I could graph out the voltage on a computer. You might think the graph would just be a straight line, constant voltage, but it's not actually. If you could graph this voltage on a computer program, you would see the voltage going up, down, up, down, up, down, up, down. And this is because the power is made in a power plant that uses a generator like this. Okay, so actually, this does not provide a constant voltage. The voltage is going up, down, up, down, up, down, up, down. Does anybody know what the frequency is here? How quickly this changes per second? How many cycles are there per second? Does anyone know this in a power plant? No? So this here, it changes. If there's 50 cycles in a second. So in 1 second, it cycles up and down 50 times. Okay? Now you actually can see that on your plug. Does anyone have a plug with them? Like a charger? Yeah, just print on it. I'll show you. Can you see here? See where it says 50 to 60 hertz?
Yeah.
Yeah. Can you see at the there, yeah, you see where it says 50 to 60 hertz. Yeah? You see that? 50 to 60 hertz. So what they're saying is you must plug it into a power supply that changes direction 50 times in a second. Okay? I think this is kind of the standard internationally between 50 and 60 cycles in a second. Okay? What's not standard is the voltage. So here in Ireland, the voltage goes on average to 20, while in America it's 110. What did you say it was? 220? Don't know? Well, let me put it this way. Do you need any special plug if you want to bring some electronics from home? No? I think it's only America that's 110. Yeah, it's between so they sometimes ask you to draw that in the exam. And we'll continue with this next time then. Wait, is there a next time? Do I have one on Friday? I have a Friday? Then we have a break. Do you want to have a mid-semester exam? Do you think? After the break? What do you think? It might help you focus to do something during the break. I could give you an exam on waves, because you finished waves. I'll give you an exam on waves, and then one topic from semester 1. Which topic would you like to revise? Okay, so I'll give you a wave and electricity exam sometime after the break then. This will help focus you with all your free time. Okay. Okay. Yeah. Did I what? I did, but I said I was going, but you were all too busy talking to the rain, so nobody noticed I left. So I just said, fine. Fine.